Here we try to explain about derived units and the names given to derived units. So generally we know, for example, the unit of force we say Newton, but Newton actually has got in terms of SI it is meter kg second square. So hertz, for example, is cycles per second, so S inverse. So for all these names, it is necessary. It helps to know what are the SI units. So I'll just try to explain how to get these SI units for each one of them. For example, some of them very simple, like the first two examples. Then we have Pascal is nothing but force. This is a pressure force per unit area. So this unit of force is Newton, meter square, and Newton again is meter. Meter kg s minus 2 then by meter square, so that's how you get m minus 1. So for joule, for example, they are all simple. So watt, joules per second, that is energy per second is watt, so joules per second, so we know what is the joule. So like that we can work out. Say volt, for example, what is volt? Volt is actually we can say Q is equal to CV. Okay, so C volt is equal to what we get, volt. This is Q is equal to CV. Volt is nothing but Q by C. So no, this will not give us this. So volt we will get from, that is a potential difference per unit charge. So what we use is energy by charge. So that is a potential difference is potential energy per unit charge. So this is unit of energy. So we get energy is joules. So joules by charge Q. So we do joules per second and charge per second. This gives us watt. This is ampere. So that is how volt is watt ampere. So this explains how to get this SI units. So similarly, Faraday is C is actually Coulomb. So that this tells us C is equal to Q by V. See, Coulomb volt. Again, we know what is volt, so we can get this. Okay. Then ohm is simply use the formula V is equal to IR. So resistance is V by I. So this is volt by ampere. Volt by ampere. So we know what is volt, and we know ampere, which is ampere itself is a standard unit, so that's how we get. So Siemens is the unit of conductance, which is inverse of resistance. Now Weber, for example, how do you get this? Weber is magnetic flux. So this is nothing but magnetic flux. We know that electromotive force is equal to magnetic flux, the rate of change. So this is volt, this is second. So volt into, so where is it? Weber, yeah. Volt into second. This is Weber. This is Weber. Okay. So we'll try to see some more. Yeah. That is Weber. Now magnetic flux density. That is actually we know that flux is equal to B dot A. This is magnetic flux density. So this flux we know, we have seen d phi by dt, you know, that is Weber is this thing. So this will be nothing but Weber by ampere. Sorry, area. B dot A, this is area, not ampere. Weber by area. So where is Weber by Weber density, magnetic flux. This is called Tesla. So which is nothing but Weber by area. This Weber by area. This is Tesla magnetic flux density. So same thing, inductance. Henry, for example, is E is equal to L di by dt. So this is Henry. So this is volt. This is second, and that is ampere. This is ampere. So volt second is Weber. So by ampere. So this knowledge will help the student to instead of dimensional analysis, one can use this and find out if something has gone wrong. So this expressing these derived names in terms of the basic standard units is helpful.